Welcome everybody to the third in this series of chromatography webinars discussing different aspects of chemistries, method development, and how we can optimize and speed up our method development approaches in our labs. So this third talk today, as Ian has mentioned, talks about how we can use different types of column screening, but then push our separations further and potentially faster by using software to help us in our approach. So this talk today, I'll talk a little bit about method development and different strategies, and about how we maximize the selectivity of our separations, in particular using a systematic screening approach. If you've listened to any of the previous webinars that I've given, you'll know that selectivity is the key to resolution, and that I'm very much a fan, and I think that screening different column chemistries can be very powerful to help you with method development. And in this particular talk, I'm going to take the screening one step further and use software to optimize for our final separation. Now, we all know, of course, that method development is the exciting part of chromatography, and it's the part of chromatography most people enjoy doing. Now, quite often, method development is an iterative process. So this means we make changes, we do some injections, we see how this affects the separation, and then based on the data and the results, we make a choice and we do more injections and more separations to see how we can finally try and get the method that we're after. Now, of course, there's lots of different ways to do method development. Some people use trial and error. They get some general conditions, do some injections and modify some parameters to see if they can get to their final method. Some people are quite systematic, and they take one parameter at a time and explore how it affects their separation. There's also other types of approaches, such as the quality by design approach, which is something that's quite popular in the pharmaceutical industry at the moment. And of course, there's systematic screening. This is where we can use different chromatography parameters, systematically screen through those different parameters and see if we can find a combination of those parameters that give us the method that we're interested in. And of course, logical and well-structured method development helps you develop your method far more productively. It also helps you understand something about the retention behavior of your analytes. So method development really is the exciting part of chromatography. Now, what I'd like to do, if you've been to any of my webinars previously, I run a couple of polls through the webinar just so that we can understand a little bit about the type of work that the audience does. So I'm going to run that first poll now. So hopefully what you should see on your screen, and I'll leave the poll open just for 1 minute or so. It would be great if you could answer the poll and click on one of those boxes, those radio buttons, either yes or no. And that will help us understand a little bit about the type of work that you do, and of course make sure that I'm giving you the right information and the right data to help you with your work. So I'll leave the poll open just for another few more seconds, and then I'll close the poll and carry on with the webinar. Okay. So thank you very much for your responses. So we'll continue with the webinar. So a systematic screening approach is quite useful for method development because we can look at specific parameters that maximize the selectivity of our separations. Now, the great thing about a screening approach is that it can also be automated to a degree. So we can set up an LC or UHPLC instrument. If we have the capability in our lab of column switches and solvent switches, then we can set up an instrument with different options for different column chemistries and different types of mobile phase elements. And of course, what we're trying to do is to screen through these parameters in a semi-automated way to try and find a combination that gives us the separation that we're looking for. Now, the great thing about a screening approach is that we can set the instrumentation up And of course, we can walk away and do some other things whilst the instrument is doing all the hard work for us. And then we can come back at a later time in the day, look through the data, and hopefully we can find that combination that gives us the separation that we're looking for. Now, of course, in the first part of this slide, I talked about parameters that maximize selectivity. So selectivity is the key to resolution of analytes in chromatography, and it's described by this equation which I've shown in each of the webinars previously, and it's a very important equation in chromatography. Now, this equation you can see brings together a component for efficiency, a component for selectivity, and a component for retention. And this equation is best described in a graphical format, and we can see now we have resolution on the y-axis. That's the resolution of our compounds, and on the x-axis you can see we have alpha or selectivity, n or efficiency, k retention factor. And we can see very clearly from this graph that selectivity is very powerful with respect to resolution. And in fact, yes, I can get the technology to work here. You can see with the little red spot that's on the screen now, alpha really is the key to resolution, and efficiency boosts performance. We can see how selectivity here is maximizing the resolution of our compounds from each other. So we now know that selectivity is really important for resolution. So which parameters in chromatography are affected or can affect selectivity? Well, if we look, actually many of the mobile phase, the column parameters, and even some instrument parameters have an impact on selectivity. So most things that you can change and modify in your chromatography system as you're developing your method have an impact on alpha. However, the key thing to remember is that not all parameters affect selectivity to the same degree. So you can see there, for instance, that we have a list on the left-hand side for isocratic separations, and we can see that the parameters of the top of that list have a bigger impact on selectivity. So the column stationary phase type, for instance, the mechanisms of interaction, the pH of your mobile phase is very powerful, particularly for ionizable compounds, and the type of organic modifier as well, whether it is acetonitrile, an aprotic solvent, or methanol as a protic solvent. These have different effects on selectivity. So that's for isocratic separations. For gradient separations, on the right-hand side of the slide, you can see that the parameters on the left are also important, but we've got some specific parameters for gradient elution chromatography. We have the steepness of the gradients, we have K star, which is the apparent retention in gradient chromatography, according to this equation, simple equation, where we have Tg, gradient time, F, flow rate. We have this symbol here, which is the gradient range. We have Vm, the column volume, and then M, which is a constant depending on your analyte molecular weight. We also have dwell volume, and we have column dimensions as well. All of these factors can affect the selectivity of your separations to a greater or lesser degree. Now, when we're developing methods, it makes sense to focus on those parameters that have a bigger impact on selectivity. This way you're maximizing the potential selectivity for your separations. You're trying to maximize alpha, as I showed you on that previous graph. Now, for this particular talk today, I'm going to talk about the stationary phase chemistries and the different mechanisms and how we can use those, and also on the type of organic modifier within a screening approach. Then, once we have that data, I'm going to optimize that further using software. So, how do we get different types of chemistries, and what does that mean, different types of column chemistries? So on the screen now we have a relatively simple aromatic ring, and if we substitute onto that ring different types of, for instance, electron donating groups, you can see that we change the properties of that ring. So we now have, for instance, a representation of a simple phenyl stationary phase. It has the potential for pi interactions through the aromatic ring. It has a low amount of hydrophobic interactions, and it has a weak dipole across the ring system. Now we can also substitute electron withdrawing groups onto the ring system. And here we have 5 fluorine atoms. So fluorine, electronegative atom, substituted 5 times onto this ring, and this is a classic pentafluorophenol type stationary phase. And we can see here that it changes the properties of the ring, and it's complementary to the simple phenol ring system. Now, what we've tried to do when we're designing these different stationary phases is to bring together the mechanisms of interaction, for instance, from a C18 column, the hydrophobic interactions, the robustness, the manufacturability, the well understood chemistry of the C18, together with the aromatic ring system of a phenol into a single stationary phase, because this has multiple modes of interaction which will maximize selectivity for our separations. And the same for the C18 PFP. It's like having 2 different types of column together in a single stationary phase. A C18, the stability, the good and robustness of that column, together with the pentafluorophenol stationary phase. And these stationary phases, they have these multiple modes of interaction that maximize selectivity. They also have low bleed, and they're also 100% wettable. So this means that you can use these 2 different types of columns in 100% aqueous. They don't suffer from poor dewetting or phase collapse. Why would that be useful? Well, if your samples contain polar analytes within the mixture, and you want to drop the percentage organic as low as possible to try and retain them in your separations, these type of columns can be dropped to 0% organic solvent and still give you reproducible retention. As an example, this is just one single example to show you how this C18 PFP column, for instance, gives you options with your chromatography. So in this first chromatogram, we can see here we have a standard C18 column, and the mixture, we've got a mixture of methoxybenzene isomers, and you can see on the right hand of the slide there that we have 3 positional isomers within this 8 compound mixture. So these are trimethoxy isomers, and they vary in the position of the methoxy group around the ring system. Now, as we would expect, and we can see from the top chromatogram where the red dot is here, we don't get separation of all the compounds in this mixture, because we wouldn't expect that with a standard C18 column. A standard C18 column is dominated by hydrophobic interactions. If we look down here at the thermo-PFP column, you can see quite a different separation profile. We can see that we've almost got complete resolution of those closely related compounds within this chromatogram, but still there's 1 or 2 co-eluting, and you can see all of the compounds elute relatively quickly because they're closer to where the injection, the T0 on the chromatogram is. There's little hydrophobicity to this stationary phase. Now with the C18 PFP column, what you can see here is we're bringing together the mechanisms of a C18 together with the mechanisms of a PFP into a single stationary phase, and you can see we get a very different selectivity. We have full separation of the compounds in this mixture. We have a broader retention window. We're effectively bringing together those different mechanisms of interaction to give us the separation that we want. So what does that mean for method development? Well, on the slide now you can see a table, and we have the different types of column chemistries in the first column, and we have 5 different mechanisms of interaction: hydrophobic binding, hydrophobic interactions, pi system interactions, dipole-dipole, hydrogen bonding, and shape selectivity. And we can see that it's possible to understand the weighting of these mechanisms with different types of column chemistries by characterizing the columns. And what I've done in this slide is included the reference. You can see the red dot down here. I've included the reference to the original paper, the Tanaka paper that was published, which described how to perform these experiments. So we've characterized the different columns to see the different weightings of mechanisms. And we can see, for instance, if we look at a standard C18, it is dominated by hydrophobic interactions. There's no aromaticity to that stationary phase, so there is no pi system interactions. There's no polarizable functionality to a C18, so there's no dipole-dipole interactions. There's a small amount of hydrogen bonding, from the silica surface, and actually most C18s contain a small amount of shape selectivity as well. Now, when people do method development, this is the most common stationary phase that they use. And that's okay, because that's what most people's experiences are. And what I'd like to do now is ask a second poll, which is C18 the most common phase that you use for your method development? I think that it is the most common phase, but of course it's always interesting to see other people's perspectives and to see what their experiences are and the types of column chemistries that you use in your laboratories. So if you could just click on one of the radio buttons, please, either the yes, that the C18 is the most column you use, or the no, the C18 isn't the most column you use, that would be really helpful. And I'll leave the poll on just for another few more seconds before I close the poll and we carry on with the rest of the webinar. Okay. Thank you very much for those who have voted with an answer. That's really helpful because it's always useful to know what people use in their laboratories. So back to the webinar. So we can see that, as I said, the C18 is the most common column, but of course, if we want to maximize the selectivity for column chemistries, it makes sense to use different types of columns. And you can see that I've got the different types of column chemistries, and more stars underneath a particular mechanism of interaction means that the weighting of that mechanism is higher for that particular column. So if we use a combination of these different columns, it means we're using the chemistry to do the work to help us maximize selectivity. And this is ideal for method development. So if we consider from a method development and screening approach, for instance, we have a C18 column, which is the most popular column typically people use, but then we have these other different types of columns with different weightings of mechanisms of interaction. So this means our analytes can interact differently with the stationary phase and then hopefully be retained in a different way. It helps us understand the complexities of our sample. And of course, these different columns are complementary to each other. That's really important too. So we have essentially a 6-column method development platform based around column chemistry selectivity. Now, of course, if you have a 6-column switcher, this is ideal, although I've seen people use 3-column switchers and also do this individually in their method development work as well. Now, in the lab that where I do method development, we actually have 6 columns and also a solvent switcher as well. So we actually have each of those different column chemistries, but together with methanol and acetonitrile as well. So that allows us to explore those different combinations of column and solvent to see if we can find a particular combination that gets us to the separation that we're looking for. So here you can see a picture of the instrument that's used in my lab. It's a UHPLC capable instrument, and you can see we have a column compartment next to the instrument with 6 columns in, and we use a typical format of 100 by 3 millimeter 2 micron. We found this to be the best format because it allows us speed for column screening, but it means we can also translate the separation to HPLC or UHPLC as necessary. So how do we do method development? So this is a simple 4-step overview of method development. Typically, we do some scouting runs with general starting conditions, and then we see what we get with the results from those data. If we need to, we would then optimize further, either for separation or maybe for peak shape, or we want a faster analysis and so on to give us our final separation. Then step 3, we can sometimes do some validation on the methods according to whatever industry that we're in, whether it's ICH, for instance, or EPA, or whatever it is that we're developing the method for. And then, of course, step 4, we actually do the analytical work, the analysis of the samples and so on. So how do we determine our initial starting conditions? Well, when we're doing some initial method development, we always perform a broad scouting gradient run, normally under acidic conditions. This is found to be the most stable area for the silica-based columns, which are the most common columns used in reverse phase chromatography, and typically for most analytes as well. How do we calculate our starting conditions? Well, this is that small equation that I showed towards the beginning of the talk. And you can see here we can solve this equation for values greater than 2 or less than 20. And the rest of the data we know, such as the column dimensions, the gradient range, and so on and so forth. And this allows us to calculate those initial starting conditions for the separation. So the first example I'm going to show you, which is a simple example, then I'm going to show you a complex example where we use software. So this first simple example is based on paracetamol, which is very well known and very well described. It's been available for many decades now in most countries around the world. Now, it's a very well-known compound, so the structures are well known and the physicochemical data are also very well known. Now, if we look at this 10 compound mixture we're going to analyze on our screening system, one of the compounds we can see we potentially have a problem in reverse phase chromatography at acidic pH. We can see that the log P value, the lipophilicity, measure of lipophilicity of this analyte, is negative. That means that this compound is extremely water soluble or very hydrophilic. But we can see if we look at the log D values, which is the distribution of different forms at different pHs, we can see that as we increase the pH, the polarity of the compound or the hydrophilicity of the compound reduces. And so for that reason, normally we would screen as a first start at acidic conditions. For that reason, for this particular analysis, we actually screened at pH 6 to give us retention of this initial compound, 4-aminophenol. So we make up the sample, the 10 compound mixture, we filter it, we put it into the vials, we equilibrate the instrument. It has all of the methods already set up with all the screening methods, all of the columns are set up. We put the sample into the instrument and we press go and we walk away. And then about 8 hours later, we come back and we have the data. So I'm going to show you the data from this screening system. So these are the data with the 6 different ACE columns. You can see from the top in red, we have C18, AR, PFP, super C18, C18 amide, and the cyano-ES. Different mechanisms of interaction, different column chemistries. If we look at, first of all, the first thing to point out is peak 2. You can see peak 2 here. This is the 4-aminophenol. So you can see that even though the K value is very low, it is retained away from the T0, so we can integrate and quantify this compound. So working at the pH 6 rather than pH 3 did make a significant difference. Now, if we look at the chromatography of the 6 different chromatograms, this is using methanol as the organic solvent. We can see, for instance, we've got areas of coelution. So at the top there with the C18, we have peaks 1 and 4 coeluting. Then with the AR, we have peak 4 eluting on the tail. The PFP, they're coeluting. The super C18, they're coeluting. And then with the polar embedded C18 amide, very different mechanisms of interaction. You can see compound 4 elutes before the parent compound. And then the last column chemistry, the cyano phase, you can see peak 4 elutes just about off the tail of the parent compound paracetamol. So different profiles for those 2 different analytes depending on the column chemistry. All of the methods are exactly the same here. The only thing that's different is the column chemistry. If we look at peak pair 7 and 8, we can see they're very well separated. And as we start at the top and work our way down, we can see they're well separated on the C18, on the AR, and on the PFP and the super C18. But then when we get to the C18 amide, you can see that actually the peak pairs switch around. So now peak 8 elutes before peak 7. So there's different mechanisms of interaction giving us a different elution profile for those 2 compounds. And then also we can see with the bottom chromatogram, the cyano column, again, a switch around in the elution order, peak 8 elutes before peak 7, but they're closer together. And then finally, peak pair 9 and 10, we can see at the top, coeluting and coeluting on the AR, just about resolved on the PFP, co-eluting on the super C18, well separated on the C18 amide and the cyano-ES. So if we count up the number of peaks resolved in this compound mixture, this 10 compound mixture, we can see that we have actually, from the screening run that we performed, 2 different column chemistries where we have complete separation of all of our compounds without any further work. So this shows you how a screening system with different chemistries can be very valuable. And perhaps an important point to make is that a standard C18 is the most common starting point for most people's method development. And you can see that we have co-elution of peak pairs 1 and 4, and we have co-elution of peak pairs 9 and 10, partial co-elution. So further method development work would be required to get a method where all those analytes are fully separated. So that's the methanol data. What about the acetonitrile data? So here we have the same 6 columns run in the same way, but this time using acetonitrile as the organic solvent. So if we look at peak pairs 1 and 4 again, you can see at the top, C18 separated, the AR separated, PFP just about separated, slightly on the tail, the super C18 separated, we have co-elution with the C18 amide, and you can see we have good separation with the cyano-based column. Now peak pairs 7 and 8 and 9 and 10 slightly start to interfere with each other here, because peak pairs 8 and 9 start to interfere. So 8 and 9 with the C18 are co-eluting, with the AR they're slightly co-eluting, they're separated with the PFP, separated with the super C18, and then also separated with the C18 amide and the cyano-ES. So we can see here that we actually have 4 options with acetonitrile as the organic solvent, where we have complete separation of all our compounds. So no further method development is required. So this shows you the value of this screening platform. We've generated 12 chromatograms, 6 in methanol, 6 in acetonitrile, and the combination of column chemistry and organic solvent can help move our method development forward. And again, in acetonitrile, you can see we still have an area of co-elution. Peaks 8 and 9 co-elute. We've got to do further method development to separate these compounds from each other. Now, the structured approach that I've just talked through there, this is actually available in a poster, which we're happy to send you. If anybody's interested, please email me or email the information that's on these slides, and we can make sure we send you out a free A2 poster. So to the second part of the talk now. So the first part I talked about chemistries and solvents and how screening is useful, and we were fortunate enough to have options where we had complete separation for the paracetamol application. So what about complex applications where you don't get options from the screening data? So what about if we need to further optimize the separation? Now, of course, when you're optimizing your separation, you can look at other parameters. So you can look at changing your gradient, you can introduce gradient steps, you can look at gradient slope, you can look at things like temperature and pH and all various other types of parameters. However, we can also use software to help us with our separations. Before I move on to that next section, the last 10 minutes or so of the talk, I'd just like to ask you another poll question based around the screening approach that I've just described. Do you think that screening different column chemistries could help you for your method development? Based on some of the information I've talked about today and the example I've shown and the concepts behind column chemistry maximizing selectivity, do you think that's something that's helpful? Something maybe you hadn't considered before, something that you would be maybe interested in thinking about the next time you do method development. So you can see there's a poll on the screen. Do you think screening different column chemistries could help you for your LC method development? Very simply, yes, you think it could do, or maybe for your applications, no, you don't think it could. So if you could vote, please. Just clicking one of those buttons that's on the screen now, in the GoToWebinar software, that would be great. It just helps us collect some useful information about the content that we're providing, and whether you think that this type of approach could be useful for method development applications in your particular area, for instance. Okay, so I'm going to close that vote now. So thank you everyone who has voted, and I'll carry on with the webinar. So what about software? Now, there's many different types of softwares that are available, and the one software that we've used and have some experience with is called ChromeSword. And this particular software can be used to, just like other types and brands of software, to model and predict and optimize separations with input data that you provide. For reverse phase chromatography, there are different options that you can explore. You can look at, for instance, as I've written on the slide here, the percentage organic, the gradient time, pH, temperature, and various other parameters as well. And this software is also compatible, just like other types of predictive software, with normal phase and ion exchange and so on. Now, with this particular software, it's quite useful because what I'm going to do for this example is use a more complex application where there's a lot more analytes for us to separate, and use the software to help us optimize that separation. And I'm going to demonstrate a very simple gradient time retention modeling approach. Now, with the software, you can input from as few as 2 initial runs, and this will then generate a simple model to help understand the retention behavior of your analytes. Now, if you add additional runs, this is going to help with the robustness of the model that you generate. So it helps you improve and validate the accuracy of the model. And essentially, I'm not going to show a step-by-step use of the model, but here's a screenshot from the software, and you can see here, so on the left-hand side, on the y-axis, we have log K versus percentage organic on the x-axis. So a very simple retention behavior based on the initial 3 runs that we inputted for this particular application. Now, what we can do is input the retention behavior of your analytes and then generate the model. And so the software will simulate the separation. So we can see on the left-hand side there, we have, I'll just use my pointer. So the red dot, you can see here, we have the gradient, and here we have the simulated chromatogram. And if you want to, you can also adjust that gradient manually. So you can do manual editing of the gradient if you want to. You can move it up and down, or you can make the gradient steeper or more shallow, and so on. And it will change the chromatogram accordingly to show you how it affects your separation. Also, the software can automatically optimize the separation for you. So that means that you input your data and you ask the software to try and determine a gradient approach that gives you separation of all the compounds of interest. So on the slide, you can see another screenshot. This is specifically for the ChromeSword software. You can see it says the number of nodes on the bottom, which is the number of different types of steps it will try and take to separate the analytes that you've inputted. So for instance, you can see 5 nodes there. What that means is you can see the different gradient steps on that grid, and what that means for your simulated chromatogram on the far right-hand side. So as an example, here we have a more complex application. I'm not going to talk in detail here like I did with the previous slide set. So you can see here we've got an application that has 3 active ingredients, and the other impurities are spiked in at 0.5% to give a 17 compound analyte mixture. So this is simulating a triple API type sample with related substances within the same mixture. The red rings indicate coelution of different analytes with the different column chemistries. So this is exactly the same approach as what I described previously. So we have here 6 column chemistries screened using a standard approach, and these are the data from each of the chemistries. So you can see this is using acetonitrile as the organic solvent. We've got coelution across all different column chemistries. So not like the more simple first example where we had separation options with some of the common chemistries. Now, if we look at the methanol data, yes, I forgot to mention here, we can count up the number of peaks resolved using acetonitrile, and we can see the C18 amide, 1, 2, 3, 4, the 5th column down has got 11 peaks potentially separated. So using acetonitrile, that's the best option that we would have to take forward. Now with the methanol data, again, you can see there is no standout option that gives us separation of all of our compounds. Again, we have coelution with all different column chemistries. And in fact, if you count up the number of peaks resolved, we have 3 options this time where we have 11 out of 17 peaks resolved. So further work is definitely needed. Now with this particular screening set, there's actually 2 or 3 different options that you could take forward for optimization. We could use the C18, the C18AR, or the C18 amides. Now, because the C18 amide resolves some compounds with acetonitrile and also with methanol, 11 compounds on both solvents, we decided to take that forward for the optimization process with the Chrome Sword software. So you can see that we're using the C18 amide with methanol as the organic solvent. So we use the 5-minute screening gradient, and we also use 10 and 15-minute gradients to input to generate our gradient model. We then optimize the separation, first of all for a linear gradient to see if we could get separation of all of our compounds, and then we allow the software to also try and predict or recommend multi-step gradients as well. So using the software, this was the optimum predicted linear gradient. So you can see the simulated chromatogram on the screen there with the 3 different APIs, and you can see that there are 14 impurities peaks to make 17 peaks within this sample. And you can see the gradient profile on the right-hand side of the slide at the bottom. This was what the software recommended would give us this particular separation. So this is the predicted chromatogram. In reality, when we ran the sample, this is actually what we got. So you can see there that the actual separation is pretty close to the predicted separation. But of course, the issue with most types of retention modeling software is modeling peak shape is quite difficult. And we can see that the parent compound there has a tail, and we can see that we've got a couple of peaks eluting on the tail. So we can see, even though the resolution value for RS1 is reported as 4.44, we can see that it's actually slightly on the tail of that main compound. If we look at the predicted versus experimental accuracy, we can see that the error is very low. So the software is predicting really well with respect to what we actually get experimentally and practically. So that was just the linear gradient. So what about the step gradient? So we defined a target runtime of 10 minutes, and we looked at 5 different step options for our gradients, which we can see here from the software. And this was the predicted gradient, step gradient from the software, and the gradient profile you can see on the bottom right-hand corner of the slide. So if we look again at what we actually get experimentally versus the predicted separation, we can see again that the peak tailing causes some coelution of the compounds based on the fact that the tailing of the parent compound isn't predicted well by software. And this is the same for all types of retention modeling software. So the question is, can we move peak 5, which is the impurity, away from the parent compound peak 4 paracetamol? Now, what we can do with the ChromSword software is that it has this option for weighting. So we can go into the software and say that the separation of peak 4 and peak 5 is really important to us. So we want to improve the separation of peak 4 from peak 5. And when we put that option into the software, you can see that this is the predicted chromatogram. It gives us even more resolution between the main compound, paracetamol, and the impurity, paraxanthine. We can also edit the profile manually if we want to. So for instance, this is the predicted gradient, but we can see it's flat at the end there. And if we want to, we can just increase that quickly to increase the speed of our separation to make the analysis time less. So you can use the software to help you predict and optimize your separation, but it allows you to edit manually as well. So when we look at this final separation, the predicted separation is on the top there, and then we can actually see the experimentally determined separation on the bottom. And you can see we've pulled away peak 4 from peak 5. So now that's a much better separation. So hopefully what you've heard today is how systematic screening is quite important and useful in chromatography. By using stationary phase chemistry, different mechanisms of interaction, and 2 different types of organic solvent, it's very powerful to explore the selectivity of the combinations of those 2 parameters. I showed you a 6-column 2-solvent platform that helps you identify combinations that hopefully get you towards a separation you're happy with. But if not, then there are options such as the software I showed you today that can help you further optimize your separation to get you where you want complete separation or resolution of your compounds of interest. So hopefully what you've seen is this combined ACE ChromSword method development solution can really help you in your lab with your applications. The brochure for this material is part of the webinar. It's available for you to download, but also I've put a website address at the bottom of the slide there, and there's more information at this site as well. So thank you very much for listening. Thank you for your attention.